Hi, hello. Yeah, so today I'm going to be talking to you about robust estimators and high dimensions without computational intractability. This is joint work with Ilyas, Gautam, Daniel, Ankuran, and Alistair. All right. So the primary topic of study in this talk will be something called density estimation, which is a fundamental problem in unsupervised learning. And roughly stated, it is the following. We let C be a fixed class of distributions, so think of having some structure, so like Gaussians or Prague distributions or log concave or something like this. Given independent samples from some unknown distribution f in this class C, can you recover f? Okay, this is the goal of density estimation. It's been, studied a lot in both our community and also machine learning and statistics. In our community, we've really focused on really complicated structural assumptions, so like, mixtures of Gaussians, learning that kind of stuff. In this talk, the focus will be a bit different. It will be on the question of robustness, or as it is known in statistics and machine learning, model misspecification, which is the observation that in the real world, we're trying to model these like complicated phenomena using our model C. So things are often well approximated by our model. That's at least what we hope, but usually never truly in our model. So there's going to be some sort of like adversarial noise that we don't know how much to control. So kind of the cartoon is as follows. So let's say we're trying to model something by a Gaussian in one dimension. More likely than not, there's going to be some subpopulation that we just kind of forgot about, and we're going to have some small bumps. More likely than not, there's just going to be noise kind of everywhere that we failed to model because they're kind of smaller order terms in general. But now we get samples from this kind of noisy distribution, which looks like a Gaussian. And the goal is to recover a good Gaussian fit still. So now the question is, given independent samples from something close to f, can you recover f? Okay? And so roughly when something's close to f, this kind of corresponds to saying that some of the samples are kind of corrupted in some sense. And to make this rigorous, we will use the following contamination model. So in this talk, we say that a set of samples is epsilon corrupted of size n for some distribution f if we generate them via the following process. First, we generate n independent samples from f. Then we give them to an adversary who is allowed to look at these samples and then is allowed to change an epsilon fraction of them in any way they desire. Okay? So for those of you who might know, this is not too important, but this is a slightly stronger notion than Huber's classical contamination model introduced back in the 80s. And now, informally stated, the goal is as follows. We're given this corrupted set of samples, and now we wish to extract as much information as possible about the original distribution, even though some of them are corrupted. All right? So let me make this, let me give you a very pictorial example. So suppose I have the following Gaussian distribution. I draw these blue samples. Each dot is a nice independent sample from a Gaussian. All right? Then I hand them to a very evil, but also very all-powerful adversary, Bill Belichick, which is head coach of the Patriots. And what he is allowed to do is he looks at these samples, and he wants to screw you up as much as possible, because that's what Bill Belichick does. And so what he does is he gets to move an epsilon fraction of them wherever they want. So he moves them over there. And now he gives back to you these samples, right? And now your job is to recover, without the colors, and now your job is to recover as much information as you can about the original distribution, even though these samples are corrupted. All right, so we want to recover, the original distribution. To make this rigorous, we need to define a notion of measure. In this talk, we will use the following natural notion of measure, known as the statistical or total variation distance, which is the TV distance between two distributions f and g is just up to this 1/2, the L1 distance between f and g, their PDFs. All right, and now I can formally state this problem of agnostic learning. So we get, again, C is a structured class of distributions, and we get an epsilon corrupted set of samples from some unknown f in this class C. And our goal is to output some f hat, minimizing the TV distance between f and f hat. Okay? And for those of you who might not be too familiar with TV distance, it doesn't matter too much for the sake of this talk, because we will be considering very fundamental distributions. And for these distributions, recovering TV distance will just mean recovering the parameters of the distribution with some appropriate scaling. Okay? So let me give a first toy example of what's going on here. So let me consider noisy density estimation in one dimension of kind of the most basic univariate distribution, which is the Gaussian. So we let x1 through xn be an epsilon corrupted set of samples from a Gaussian in one dimension with mean, mu, and variance sigma squared. And the goal is to learn this Gaussian. Okay? In fact, let me simplify the problem a lot. Let me assume the variance is given to you to be 1. Okay? So now your job is just to recover the mean as well as you can. Okay, how would you do this? Well, if the samples weren't corrupted, then what you could do is just take the empirical mean of the samples, and then by classical tail bounds, this does as well as you could possibly hope. But does the empirical mean still work in this setting? Well, hopefully you can figure it out. The answer is no for the following kind of dumb reason, which is that our adversary Bill Belichick can just move a point to plus infinity. Right? Then the empirical mean of the corrupted points is like arbitrarily far away from the truth, as much as you want. But it might not be too surprising that something else does work in this setting. The empirical median is a robust estimator in this setting. Okay, and this is made rigorous by the following fact. Given an epsilon corrupted set of samples from a Gaussian with mean mu and variance 1 of sufficiently large size, then with high probability, the distance between the true mean and the median of the samples is at most O of epsilon. And this turns out to imply that the TV distance between the truth and what you recovered is also at most O of epsilon. And it turns out that this error is optimal up to constant factors. Similarly, if you want to recover the variance, something called the interquartile range works for recovering sigma squared in the presence of this noise. Okay. So what this says is that the median and the interquartile range are robust statistics for the mean and variance, respectively. And the study of such statistics, which still function and approximate things non-trivially in the presence of this adversarial noise, is a very classical and very natural subfield of statistics dating back to the 70s and 80s, and there's been like a bunch of research in this area, a bunch of books written about it as well. Okay, but fast forward a couple decades, and these median and interquartile range were kind of nice in the 70s and 80s, but now what do we really care about? We really care about high-dimensional statistics, because for the simple reason that nowadays many natural machine learning applications really involve extremely high-dimensional data, so like I'm thinking like millions and tens of millions of dimensions. Unfortunately, in this setting, when the dimension is very high, robust statistics are very poorly understood. So for instance, consider the following problem, which is just a natural generalization of the 1D problem that I posed to you before. So we're given an epsilon corrupted set of samples from some d-dimensional Gaussian. Now it has a mean vector mu and a covariance matrix sigma. And now your goal is, as before, recover mu hat and sigma hat, recovering the truth and TV distance. Okay? So this is actually like one of the problems that we consider in this talk. This is in this paper. Turns out this problem was surprisingly poorly understood. To illustrate this, let me like vastly simplify the problem and just tell you the covariance's identity, just like I did in one dimension. So all you have to do is recover mu. It turns out the correct metric is the L2 norm. So you just need to recover mu in Euclidean distance. Okay? So yeah, this problem has been like studied a lot, but surprisingly, all the questions that we had at least prior to like this work were surprisingly unsatisfactory. All right, so let me just kind of give you a list of these things. So recall that in one dimension, if you want to recover the mean, all you had to do was take the median. Unfortunately, in high dimensions, there's no good generalization of the median. This is kind of like the major problem. So for instance, there's something called the Tukey median, which was developed by statisticians back in the 70s. And this works great, actually. The error guarantee is O of epsilon. Okay, so this is actually optimal. This is great. Unfortunately, the runtime of computing this Tukey median, it's NP hard. It's hard and hard to approximate as well. And all our algorithms that we know of how to compute the Tukey median take time, which is like exponential in the number of dimensions. So this is really bad. There's another notion of median, which is called the geometric median. And the runtime of this, you can compute this in polynomial time. In fact, actually nearly linear time as of this year. So this is nice. But the error guarantee is bad. It's O of epsilon root d. And this root d factor is really killer. Particular, when d is millions and tens of millions, it turns out that if you have an error guarantee of this, then you really don't get any non-trivial statistical guarantees. So yeah, this is bad. And pretty much what happens was that, all known algorithms kind of fell into one of these two camps. Either their error was great, but their runtime was bad, or their runtime was polynomial time, but they lost, root d factors or worse in their error. So for instance, there's an algorithm called the tournament, which gets, again, the right error guarantee, but the runtime is, again, exponential in the number of dimensions. There's another algorithm called like naive pruning, which you can implement in like nearly linear time or linear time. But the error guarantee is, again, epsilon root d. And then finally, there's a very popular algorithm in practice called ransack, which you can, again, implement very efficiently. But as stated, technically, their error guarantee is like infinite. I mean, whatever, it's not too important. The point is that all known robust estimators for the mean and high dimensions are either computationally intractable to compute, or they lose this dimension-dependent factor in the error, this root d factor or worse. All right, so this poses a kind of natural question to us. Can we avoid this trade-off? Can we agnostically learn high dimensions efficiently with no dimension dependence in the error? And the main result of this talk is yes, this is indeed possible. Okay, so one of our results is the following. So there is a polynomial time algorithm which, given an epsilon corrupted set of samples from a Gaussian with mean mu and covariance sigma, so neither of these are known to you, a sufficiently large size, outputs a mu hat and sigma hat such that with high probability, the TV distance between the true Gaussian and what we output is the most this quantity. So it's O of epsilon log to 3 halves, 1 over epsilon. In particular, there's no d factors at all, not even like log d factors. And this error is optimal up to these polylogarithmic factors. Okay, and I want to mention briefly, I'm not going to really talk about sample complexity this entire talk. So I just said sufficiently large size. It turns out actually our sample complexities are quite nice. In fact, one algorithm we give gets like almost optimal sample complexity, so or nearly optimal sample complexity. Okay. I also want to mention there is a related work by Lai, Rao, and Paula, which is actually going to be presented in the next talk in this session. And they actually give results for a very related problem, which is this problem pretty much cast in a more generalized setting. I don't want to get into a discussion of these right now, but if you're interested, I can kind of give you some comparisons offline. All right. We also give more efficient robust learning algorithms, which kind of extensions of the algorithm we present for Gaussians, but they're very non-trivial. So here's kind of like a full table of what we do. So this is the Gaussian result. We also can learn product distributions over the hypercube, mixtures of two balanced product distributions, and mixtures of case spherical Gaussians. And for all of these, so for these, the runtime is polynomial and everything. For this one, this matches the best runtime known for not agnostic algorithms. And for all of these, we get, these are not quite information theoretically optimal, but they are still dimension independent. And these guarantees are highly non-trivial to obtain, actually, and very interesting, in my opinion. All right, so for the remainder of this talk, let me just focus on kind of giving you some intuition on how to learn the mean robustly, or how to do this, how we're going to do anything. So let me just focus on the problem of learning the mean of a Gaussian. So let me kind of first give you some intuition for why simple algorithms kind of don't work. So why does the following simple algorithm fail? Which is just remove all points from your sample set, which are obviously too far away to be from the true Gaussian, and then hope that you removed all outliers and then take the empirical mean. Okay, so why does this fail? Well, here's kind of like the cartoon version of why this fails. So in constant dimensions, we think of points from a Gaussian as being nice and centered around the mean. So what this says is that all points from the true Gaussian can't be more than maybe like O tilde of 1 away from the mean. And so if the bad points want to hide within and look like a good point, their norm can also not be more than like logarithmically far out from the mean. And so when you take the empirical mean of these points, the error they can do, well, there's only epsilon fraction of them, and each one of them has at most logarithmic norm. So their contribution to the error is at most, O tilde of epsilon. So this is nice. But in d dimensions, what happens is that when d is high, points from a d-dimensional Gaussian concentrate very tightly in this kind of donut of radius root d around the mean. All right, so that means that what the adversary should do now is hide their points within this ring of radius root d as well. And then each one of these points will look just like a Gaussian individually. And now you have, an epsilon fraction of points, which are these adversarial points, each one of which is root d far away from the truth, and that's how you get this epsilon root d error. This is why naive pruning is going to fail for this problem. So hopefully that makes sense. Hopefully I've kind of argued for you that, at least at some moral level, any method that only looks for outliers at an individual basis must get stuck at this epsilon root d barrier. Okay, and the way to get around this is you kind of have to use, you have to kind of find outliers at some global sense. So intuitively, an outlier is not just an outlier by the way that it acts independently, but also it must be an outlier by the way it interacts with its nearby points. If there's too many points in some direction, they must all collectively be in some sense outliers. We make this rigorous in the following notion, in the following kind of informal idea. If the corrupted points move the empirical mean by more than O tilde of epsilon, then they must also scope the empirical covariance in a way which is very visible. is what we mean. So given an epsilon corrupted set of samples from a Gaussian with mean, mu, and variance identity of size this, don't worry too much about it, form the empirical mean and empirical covariance of these data points, okay, of these corrupted set of samples. And then what we have is the following. With high probability, if the distance between the true mean and the empirical mean is too large, much larger than it could be without corruptions, more than omega of epsilon square root log 1 of epsilon, then what happens is that the spectral norm deviation between the empirical covariance of what it ought to be, which is the identity, is also much larger than what it could be if there was no noise. It has to be at least this. So what this is saying is that the only way the adversary can screw up the empirical mean, whatever they do, if they screw up the empirical mean by more than could possibly be from noise, just from Gaussian noise, then they must also screw up the empirical covariance in a very visible way. And therefore, the empirical covariance, the spectrum of the empirical covariance gives us kind of a certificate of whether or not the adversary has screwed up the mean. Okay? So hopefully, I'm not going to prove this statement, but what this statement says is that we can detect whether or not the empirical mean is off from what it ought to be just by checking the spectrum of the empirical covariance. Okay? There's more ideas needed to make this actually algorithmic, which I will not get into, but we give two algorithms motivated by this kind of intuition. The first is a filtering or rejection sampling kind of algorithm, which runs in time which is O tilde of n d squared, where n is the number of samples. So it's actually pretty efficient. We actually implemented this. It's actually quite fast. But this n that you need to get more guarantees is a bit larger than the information theoretic optimum. So it's not quite sample optimal. There's another algorithm that we have, which is called convex programming, and this runs in polynomial and everything time, but it's like really like a theorist polynomial, so it's like you can't really implement this. However, it is considerably more careful as far as we can tell with the samples, so it is nearly sample optimal. But kind of the shared intuition between these two things is that, okay, if the spectral norm between sigma hat and the identity is large, then this can only mean that in the direction in which it is large, the top eigenvector, this direction can only have large variance because the bad points are in this direction. Because if the bad points weren't in this direction, then we know by Gaussian concentration everything would be fine. So in that sense, in this direction of the top eigenvector, the bad points must in some sense dominate. And so we can use this to just prune out kind of bad points or like weaken their influence in some sense, and this allows us to make some algorithmic progress. All right, that's all I'm going to say about unknown mean. Let me now go to unknown covariance very briefly. At a high level, we have very similar ideas. So let me assume that the mean is 0, so all we need to do is recover the second moment. So recall that for empirical mean, the idea was that if the bad points move the empirical mean by more than O tilde of epsilon, then they must also screw up the empirical covariance. Or in other words, if they move the empirical first moment by a lot, then they must also screw up the empirical second moment. Kind of the same idea kind of works for empirical, for covariance, which is that if they move the empirical covariance by more than O tilde of epsilon, or a second moment, then they must also screw up the fourth moment in some noticeable spectral way, which I will not get into. And intuitively, the ideas are kind of similar, but the techniques are a bit more complicated because these objects are a bit more complicated. We also give these results for Prague distributions. I'm not going to really discuss them, but at a high level, Prague distribution is just a distribution where each coordinate over the hypercube is just a distribution where each coordinate is independent. It is also determined by the mean vector. And just like for the unknown mean, we can learn, for the Gaussian, we can also learn the mean to error O tilde of epsilon in L2 norm. Unfortunately, unlike in the Gaussian case, this does not quite suffice to learn the mean of the Prague distribution. Like if there are coordinates near 0 or 1, then this is not quite okay. So you need to use something called chi-square distance. And this is a bit lossy, so we only get square root of O tilde epsilon close for general distributions. We also have similar results for mixtures. These are morally, again, similar, but they're a bit complicated, so just see the paper, please. Let me leave you with some kind of preliminary experiments. So what we did here was this is for unknown mean Gaussian. We made some sample points from some Gaussian with spherical covariance, and then we corrupted an epsilon fraction of them. And we fed them to popular algorithms and our algorithm, and we measured the distance between the truth and what we output. And you can see that for the popular algorithms, really their error does skyrocket as d goes infinity, but ours stays very constant. All right, so let me leave you with some open problems. So I showed you kind of some experimental evaluation, a very interesting question. would be a more rigorous experimental evaluation. In general, can we make these algorithms sufficiently practical to use them? Another interesting question is whether or not we can explore more distributions in more general settings. So kind of the West Coast half of our author group has already explored Bayes nets with known structure and learning of that robustly, and I have some results on robust sparse estimation. Another interesting question, I think, is can we remove these log factors from the error? They don't seem like they should be there. Can we get error O of epsilon? And finally, I mentioned that we have these two algorithms, one which is sample optimal but slow, but polytime, and the other one which is fast but takes more samples. Can we also avoid this trade-off? Can we get nearly sample optimal algorithms more efficiently? Okay, that's it. I mean, in general, the experience that we've had in high dimensions is that density estimation is really not generally the right approach. Is that you lose a lot of degrees of freedom by doing this in high dimensions. But perhaps, I don't know. Sorry, what? So it turns out that it suffices to just like flatten it into like a n squared by or d squared by d squared matrix and take some spectral properties of that. Things that are it's like it's kind of the same idea. It's a bit more complicated. It's just like whether or not there exists degree 2 polynomials of Gaussians whose like variance is too high. It's roughly speaking what's going on. Yeah. If they have different variances, this actually could be a bit tricky, I think. Yeah. Yeah. Right. So I mean, so indeed, we actually give something which approximates a Tukey median for this distributional problem because the Tukey median is close to the mean, and we are close to the mean as well. So for this, distributional setting, we are actually giving an approximation for the Tukey median. But in general,